Okay, here's a collection of questions from matric 2014 to matric 2020, the paper 2 questions on reaction rate. And also there are some questions on specific catalysts in here that relate to fertilizers. As of 2020, fertilizers are removed from the curriculum, so don't worry about some of the specific catalyst questions, but I will go through them anyway. Okay, so let's start. Which one of the following describes the effect of a positive catalyst on the net activation energy and the heat of reaction of a specific reaction? Well, if we look at those course of reaction curves, what does the catalyst do? The catalyst lowers the activation energy, and if it's a positive catalyst, it's going to decrease the activation energy, so it's going to be one of either B or D. It is going to be D because nothing changes the delta H. Remember the delta H, this is a badly drawn graph. The delta H is the difference in energy between the energy of the reactants and the products, and the catalyst just provides an alternative pathway. It does nothing to the difference in energy between the reactants and the product, so the answer here is D. Now this one says the rate of a chemical reaction is most correctly defined as the time taken for a reaction to occur. The speed at which a reaction takes place, it's kind of this one, okay? Change in amount of reactants or products, it's kind of this one as well. But this one is the winner, the change in concentration of reactants or products per unit time. Remember, per unit time is the most important, as well as change in concentration. So let's have a look at the next one. It says equal amounts of magnesium powder react respectively with equal volumes and equal concentrations of hydrochloric acid and sulfuric acid as shown below. The magnesium is in excess. That means when this reaction's finished, there's going to be a little bit of reaction left. Consider the following statements regarding these two reactions. Now, before we look at the statements regarding these two reactions, let's actually just figure out what's going on here, okay? Because reaction rate is going to be dealing with the change in concentration of reactants and products with time, okay? So if I have magnesium plus hydrochloric acid and I make a balanced reaction, I'm going to get magnesium chloride plus hydrogen gas, and to balance this I need 2 hydrochloric acids, okay? If I have magnesium and sulfuric acid, I'm going to get now magnesium sulfate and hydrogen gas, and this is already balanced, okay? So I need 2 moles of hydrochloric acid per 1 mole of magnesium, and I only need 1 mole of sulfuric acid per mole of magnesium. So this is one thing to take into consideration. The other one is, if we look at the dissociation reactions of hydrochloric acid, this goes to H plus plus Cl minus. I'm not putting in the aqueous symbols. Remember, H plus is the same as H3O plus, okay? H2SO4 dissociates into 2H plus plus SO4 2 minus. So if we look at these 2 tubes of acid, this one that's got the sulfuric acid in has got twice as many protons as this one's got protons. So this reaction's actually been driven by the protons. So this one is actually technically more concentrated. Test tube Y with the sulfuric acid is technically got a higher concentration of acid than the test tube A, because this is a diprotic acid. Sulfuric acid is a diprotic acid, and hydrochloric acid is a monoprotic acid. So if we look at the initial rate of reaction, test tube Y is going to be faster because there's a higher concentration of protons. So the initial rate of reaction in test tube X and test tube Y is not actually going to be equal. After completion of the reaction, the mass of magnesium that remains in test tube X will be greater than in test tube Y. No, this is not going to be true because we've actually put in more moles of hydrochloric acid to get the same amount of product out. So question 2, no, wait, am I talking nonsense? Let me have a look here. After completion of the reaction, the mass of magnesium, I think I was talking nonsense, that remains in test tube X will be greater than in test tube Y. Okay, I'm not sure about this one. Let's check at question 3. The amount of hydrogen gas formed in X is equal to the amount of hydrogen gas formed in Y. No, this is not going to happen because the ratio here of hydrochloric, if we look at the hydrogen gas ratio, hydrogen to HCl, this is 2 is to 1. But if we look at the ratio of hydrogen to sulfuric acid, this ratio is 1 is to 1. So this last one is not going to be true. 3 is not going to be true. Let's go back to 2 again. After completion of the reaction, the mass of magnesium that remains in test tube X will be greater than that remains in test tube Y. That should not be true. This question should be B only, 2 only, because of your ratios here. In test tube X, test tube Y, if the reaction goes to completion, okay, I can easily explain 1 and 3, yes. The memo says the answer is 2B only. With this one, I think you would have to do a bit more of a calculation. I don't have a swift answer for you, but the rate of reaction definitely depends on the proton concentration, so that one's definitely wrong. And the amount of hydrogen gas formed, this one's definitely wrong because of the mole ratios from the balanced equation. The mass of magnesium remaining, I think we should be, what's the ratio? 1 of magnesium to 2 of hydrochloric acid, 1 of magnesium to 1 of sulfuric acid. Okay, we would have to do a calculation. I can't give you an easy answer for that one. I'm sorry. Never mind, let us move on. I'll have to think about it and come back to it, yes? Okay, let's look at number 4. The potential energy diagram for a chemical reaction is shown below. Consider the following statements regarding the graph above. Okay, so first of all, if we look at this graph, we know if we look at the change in energy between the products and the reactants, this one, the delta H, is positive, so this reaction is endothermic. So before we do anything, we know we've got an endothermic reaction. Then it says to X is over here, represents the potential energy of the products formed during the reverse reaction. Okay, so the reverse reaction goes in this direction. So that is actually true, okay, for all it looks weird because it says the reverse reaction. Then it says the graph could be a representation of the change in potential energy for the following reaction. I'm not interested in the reactants and the products. I'm interested in the delta H is greater than 0. This is true. It can be positive. The graph could be a representation of the change in potential energy for the combustion of methane. The combustion of methane is always exothermic. This is like burning methylated spirits. So it cannot be 3. So I'm left with 1 and 2 only, which is A. Okay, if we look at 5, activation energy can be best described as the minimum energy to cause effective collisions. This looks promising. Make reactant molecules collide. No, they will collide according to the kinetic molecular theory regardless. Change the orientation of reactant molecules. No, things are random. A catalyst sometimes does this, changes the orientation of reactant molecules. Increases the kinetic energy. No, this is nonsense. Temperature increases the kinetic energy of reactant molecules. So activation energy is the minimum energy required to cause effective collisions, A. Now number 6, this question's out of the curriculum as of 2020, but this is a straight memory question. The flow diagram below shows 4 stages, stage A, B, C, and D in the conversion of sulfur to sulfuric acid. At which stage is the catalyst needed? Okay, this is stage B, to turn sulfur dioxide into sulfur trioxide. Remember, this is the contact process for those of you who have done fertilizers. Okay, question 7. Which one of the following sets of values for activation energy and heat of reaction is possible for a reaction? Okay, so now to answer this question, we kind of have to look at these graphs. You know, these graphs for course of reaction. I'm not labeling my axes. Please be a bit chill about it. Okay, so I've got my endothermic reaction and I've got my exothermic reaction here. Okay. Which one of the following sets of values for activation energy and heat of reaction is possible for a reaction? So if we have a look here at these two, this is where my delta H belongs, which is my heat of reaction. It comes between the reactants and the products. This is where delta H goes. Okay, that's a terrible H, sorry about that. And where does the activation energy belong? The activation energy belongs from the reactants to the peak. Okay, activation energy always goes from the energy of the reactants to the top of the hill. So if we have a look at these values, okay, if the activation energy always has to be positive. So if we look at this one and we say, if we were drawing the graph, okay, here we would have a certain amount of energy for our reactants. The activation energy will go up 100, okay? But if the heat of reaction is positive 100, I have to have this reaction here. Did I label these reactions wrong? Oh, calamity, I have labeled these reactions wrong. Okay, this one is my exo. And this one is my endo. Sorry about that, people. Okay, let's go back to what we were drawing here. If we are going to form a reaction rate graph here, the activation energy goes from my reactants up to my maximum activation energy, and then it goes back down to the heat of to the products. Okay, and so we can either jump off on one of these 2 points for endo or exo. If you go up 100, you cannot have a positive 100 heat of reaction because there has to be a difference. Look at my endothermic graph. The activation energy has to be bigger than the delta H for an endothermic reaction to occur. Okay, so this one cannot happen because the activation energy is the same as the heat of reaction for an endothermic reaction. And the first step in any reaction is always endothermic. So this one is also not possible. If we look at B, if we go up 50 and we go up a further 100 for an endothermic reaction, you're actually just getting higher and higher and higher. Your delta H is bigger than your activation energy. That can't happen. This one with 50 and 50, the same logic applies to the 100 and 100. It's not going to work. You have to have an activation energy with a heat of reaction that is either less than the activation energy or a lot more. So can you see here, if we look at my exothermic graph, which I had initially mislabeled, this delta H can easily be negative 50, okay? And this delta H could be positive 50, but in both cases, the activation energy will be a different value. So the answer here for number 7 is going to be D. over here, because we can start on the axis, we can go up 100, but for the delta H to be negative 50, we're going to come back down, and this here is going to be minus 50. Note this graph is not drawn to scale. And this here is going to be positive 100, and that graph will work. We will be absolutely fine. Okay, now number 8 is a memory question for fertilizers again. Which catalyst is used in the Ostwald process? It's platinum, number C. Now number 9, consider the following potential energy diagram for a chemical reaction. If we look at this reaction, we know this reaction's endothermic. Which one of the following shows the values of total energy change? Total energy change, we call this delta H, activation energy EA. So basically they just want you to read this off the graph. They're checking, do you know that from the reactants to the peak is EA, and from the reactants to the products is delta H. So if we read delta H off the graph, the difference in energy between the reactants 20 and the product 60. The difference between 60 and 20 is 40. So we're looking for an energy change of plus 40. If we look at the activation energy, it's between the reactants, which are at 20, and the peak of the graph, which is at 100, and this is now 80. So this one is the correct one. If we look at delta H, it's final minus initial, and this is final, this is initial. 60 minus 20 is positive 40. The answer is C. If it was D, this would be an exothermic reaction, and the graph would dip below 20 to like negative 20 on that axis. Now here we've got number 10 here. Graph Q, the solid line. Okay, can you see this is the solid line over here? Here is Q, this one. Was obtained for the reaction of 100 cubic centimeters of 1 mole per cubic decimeter hydrochloric acid in solution with excess magnesium powder. If there's excess magnesium powder, the reaction will run to completion. Which of the graphs A, B, C, or D probably represents the reaction of 100 cubic centimeters, okay, same volume, of 1 mole cubic decimeter, same concentration, ethanoic acid, this is ethanoic acid, you should know that, with excess magnesium powder. So if we have a look here, these are both monoprotic acids, okay? So HCl plus magnesium will go to magnesium chloride and hydrogen gas, and I need 2 of these to balance it. And ethanoic acid, okay, plus magnesium will go to magnesium ethanoate. Okay. Why am I putting the brackets around that? Clearly it's late in the day. Okay, I need 2 of these to 1 of those, and hydrogen gas. And this means I need 2 of these. Okay, so basically it's the same reaction, and both of them have the same ratio for the volume of hydrogen gas produced. But we know that hydrochloric acid is a strong acid, okay, and ethanoic acid is a weak acid. Ethanoic acid is in equilibrium. So according to the balanced equation, the mole ratio is the same, so we will produce the same volume of hydrogen gas. So we're looking at a graph that should end up on the same completion line as graph B, okay, because my initial concentrations of the acids are the same. But because vinegar, when it makes its protons, it is an equilibrium reaction to the dissociation into its ions. What's happening is, as the reaction starts, okay, there are few protons available to react because it's a weak acid, but as you remove them from solution as hydrogen gas, the forward reaction is favored and you will keep producing protons. But because in the beginning it wasn't completely dissociated, there is effectively a low concentration of hydrogen ions, which means the reaction rate will be slower. So graph C is going to be the correct graph, okay? Because why? It shows a slower rate of reaction, which we would expect because ethanoic acid is the weak acid, but it shows the same amount of products being formed as reaction Q, and so and based on the balanced equation and the concentration of reactants, we should end up with C. Okay, so A is wrong because we can't produce more gas, B is wrong because it's faster, and D is wrong because we don't make enough gas. So we want to make the same amount of gas but slower, and that is curve C. Okay, number 11 is the definition. The boiling point of a compound is the temperature at which its vapor pressure equals atmospheric pressure. The energy change during a chemical reaction is known as what? For number 12, energy change, this is delta H. It is also known as B, the heat of reaction. Activated complex is something that forms at the peak of the graph. Activation energy is the minimum energy required for an activation to occur, and bond energy is the energy that exists between two atoms in a chemical bond. So it's got nothing to do with the chemical reaction A. Okay, number 13, this is an endothermic graph as well. The potential energy graph for a hypothetical chemical reaction is shown below. Okay, and so we've got A, the energy of the reactants, B, the energy of the products, and C, the energy of the activated complex. So it says to you, what type of reaction is taking place? Okay, we know this is an endothermic reaction because delta H is positive. Okay, so we're going to immediately rub out A. If you can't recognize these graphs, you have not been doing your homework. And we're going to rub out D because they are wrong. How do we find delta H? We take products minus reactants, which is B minus A. And to find activation energy, it's the peak of the graph, C, minus the energy of the reactants, A. So my answer here is B. It's an endothermic reaction. Delta H is B minus A. Activation energy is the peak of the graph minus the energy of the reactants. Okay, study the hypothetical reaction below. The rate of reaction in terms of the number of moles of substance P used up is this. Okay, so what is this? P is a reactant. P decreases at 1 times 10 to the negative 3 moles per cubic decimeter per second. I'm not writing it out. What is the rate? It's the same units at the which product R is formed. Okay, so now if we have a look here, P and R, okay, if we have a look at the ratio of P to R from the balanced equation, it is 2 is to 4. So every time we use up 2 moles of P, we produce 4 moles of R, which is the same as a ratio of saying for every 1 mole of P we use, we form 2 moles of R. So as the one gas is being used up, the other gas is being formed in actual fact twice the volume, okay? Twice the number of moles that are in the fixed container per cubic decimeter per second. It is going to end up being twice the reaction rate, which is answer D. Now number 15, consider the balanced equation for a chemical reaction below. 2 nitrogen monoxide plus oxygen goes to 2 nitrogen dioxide. The activation energy of the forward and reverse reactions are this, what respectively. Okay, let's draw the graph. Okay, and it says to you the activation energy. The The activation energy of the forward reaction is 156 and the backward reaction is 175. That means the backward reaction is bigger than the forward reaction. Okay, remember, activation energy goes from the reactants to the peak of the graph. Goodness, this is a terrible graph. Okay, this is going to be the EA of the forward. Okay, and this is going to be the EA of the backward. Okay, and this one is 175 and this one is 156. Okay, so the backward reaction is harder, takes more activation energy than the forward reaction. Now it says to you, what is the heat of reaction? Well, if you look at how this is drawn on the graph, we're going to say 175 minus 156, and this is going to give us, what's that? That gives you 19, yes, but it is minus 19 because the activation energy for the reverse reaction is larger. You can see on this graph here, this is going to be minus 19. 156 plus 19 gives you 175, but the reverse reaction is from the products to the reactants, and it was harder to achieve. So number 15, the answer is A. Okay, number 16, the temperature of a substance is a measure of B. This is a definition, the average kinetic energy of the particles. Because remember, all the particles in a liquid have different kinetic energies, and when we measure the temperature, we take the average. Because remember, the particles are colliding into each other all the time, and when they collide into each other, they swap their energies. Okay, number 17. In a chemical reaction, the difference between the potential energy of the products and the potential energy of the reactants, this is delta H that they are talking about. Okay, so now A looks quite promising. Enthalpy of the reaction. Okay, rate of reaction, no, that's the change in concentration of reactants or products per unit time. The enthalpy change of the reaction. Ooh, this one looks a lot better than A because it said to you in the question the difference. So to find the difference, we subtract. So it's EP products minus EP reactants, and this is in fact delta H, which we call delta is showing you change. So this answer is C. The total potential energy of the particles, oh, that's nonsense. Okay, that has got more to do with the bonding than the change that's been described. So that answer is C. Now consider the reaction represented by the balanced equation below. A2 gas plus B2 gas goes to 2AB. The activation energy for the forward reaction, so let's draw this. The activation energy for the forward reaction is 180. Okay, and the reverse reaction, so remember these are reactants going to products. This is a bigger value. The reverse reaction is when we go from products to reactants. This one is now 200. Okay, so this is EA backwards, and this one is EA forwards. The heat of reaction. The heat of reaction is the difference in energy between the reactants and the products. And if we look on these two graphs, the difference between 180 and 200 is 20. Okay, but this is an exothermic reaction because the reverse energy's activation energy is bigger. So the answer here is B, negative 20 kilojoules. Okay, the equation below represents the decomposition of calcium carbonate. Calcium carbonate solid goes to calcium oxide plus carbon dioxide gas. Which one of the following factors will increase the initial rate of decomposition of calcium carbonate? Okay, so this one is a solid. Look at the state symbol. So how to make something change rate of reaction? We have to either if it's a solid, we can increase the surface area by powdering it or dividing it or something. We cannot do pressure because it is not a gas, okay? This is a forward reaction. It's not an equilibrium reaction. It's a reaction that the products do not go back to form the reactants easily. So we can't look at anything to do with gas pressure because it's not an equilibrium reaction. Temperature, yes, will increase the rate of the reaction. We cannot look at concentration because it's a solid, and the mass is not going to make any difference. It is only if that mass has been powdered or granulated or something. So the answer is B. Okay, number 20, the activation energy for a certain reaction is 50 kilojoules per mole. Energy is absorbed. If energy is absorbed, it is endothermic. Okay, so if we draw an endothermic reaction rate curve, it will look something like this. Okay, remember here, the delta H here between the reactants. Here's the reactants, here's the products. This delta H is positive, okay, and my activation energy is going to be over here, EA. So if the EA is 50, then delta H has to be smaller than 50, okay? Delta H, oh wait, let's read the question properly. It says, which of the following is correct for the reverse reaction? So if the forward reaction is endothermic, the reverse reaction is exothermic. That is when the products return to the reactants. So now what does this activation energy for the reverse reaction look like? It's from the products to the peak. Okay, this is a smaller value than 50. So we need, for the reverse reaction, we can't have an activation bigger than 50 because it's an endothermic reaction. So we're going to scratch those two out. What have we got left here? For the reverse reaction, it will be exothermic, so delta H will be less than 0. So this one is C. The activation energy is less than 50 for the reverse reaction, and the delta H is less than 0 because the reverse reaction of an endothermic reaction is exothermic. They are like the mirror images of each other. Okay, we're nearly at the end here. A potential energy diagram can be used to show the activation energy and heat of reaction. Which one of the following combinations of EA and delta H cannot be obtained for any reaction? So if they say any reaction, they are not telling you if it is endo or exothermic. Okay, so this one is exo and this one is endo. This is correct this time. Okay, so have a look here. Can we fit these values in? If we go up 50 and down 100, yes, we can do that. This one, conceivably, EA over here could be 50 and delta H could be negative 100. Okay, so A can work. Okay, so it's not this one. Can we go up 50? Because remember, EA goes up, and then up 100. No, we cannot do this. This is looking like my likely answer. Let's just check. Can we go up 100? Can you see here? We went up 100. And then have a difference of 50 between the reactants and products, positive 50. Yes, we can do this. In an endothermic reaction, we can have a larger EA than delta H. So this is possible, and it said what is impossible. Can we go up 100? Yeah, and then down 50. This is also an exothermic reaction. We can do that. The answer is very definitely B. Now number 22. The graph below represents the change in concentration of a reactant against time for a chemical reaction. In which one of the following graphs does the dotted line show the effect of a catalyst? What does a catalyst do? It increases reaction rate. Okay, so in this instance, it's going to change the steepness of the graph. But what else is important? It does not affect how much product, okay? It does not affect the amount of the product. It just affects how fast you get the reaction to run to completion. So these two have got different initial and final concentrations of the reactant. Okay, so if it's not affecting the amount of product, it's also not affecting the amount of reactant. Sorry, I forgot this was a reactant graph. So these two are out straight away. Okay, so what is happening? We are speeding up the graph. The amount of concentration of the reactant is going to decrease faster. So this one has to be A, because the dotted line is steeper than the solid line. So B is out as well. The answer is A. Okay, number 23. Which one of the reaction rate versus time graphs below best represents the reaction between magnesium and dilute hydrochloric acid? So this is this reaction. Remember, it's going to produce hydrogen gas, and we need two of those to balance it. Okay, so it says to you reaction rate and time. Okay, but it also says to you excess dilute hydrochloric acid. If one of the reactants is in excess, the graph has to go flat. Okay, so here, which graph is going flat? What will happen when we have a reaction? Does reaction rate speed up with time or slow down with time? Reaction rate initially starts off very fast, okay, and then slows down as time goes by. So B is obviously wrong, okay, because that's an increasing graph. We can't get the reaction rate to increase. D is also increasing graph, so we can't use D. This graph, you might be confused, yes, because if you had a change in concentration of products graph, a change in concentration of products graph can look like this, but this is not. This is a reaction rate graph. How fast are my products being produced, not how much, okay? So if we look at the reaction rate, we need a fast initial rate, which slows down, and eventually one of the reactants is in excess. The reaction is going to go to completion. There will be a zero reaction rate. So this one, remember, this is a non-reversible reaction as well. This one could happen in an equilibrium reaction, but this is not an equilibrium reaction. This is a forward reaction only. So this one can't be considered for something that's a forward reaction only. Okay, 24. The energy changes represented by P, Q, and R on the potential energy graph below take place during a reversible chemical reaction. Which one of the following changes will decrease both P? Okay, so P is effectively the activation energy, because why? It goes from the reactants up to the activated complex up top here. Okay, and then it says change P and R. Okay, now this R is the activation energy for the reverse reaction. So they're asking you to change P and R, but leave Q, which is the delta H, the enthalpy. Nothing is going to change this unless you do something weird to the reactants and products. So this one, how would I change both of these? I would form an activated complex with a lower energy. How do we do that? We add a catalyst B. Okay, and finally 25 and 26, both of which came from the November 2020 question paper. It says zinc granules react as follows with excess hydrochloric acid as shown below. Zinc plus hydrochloric acid goes to zinc chloride and hydrogen gas. Which one of the following combinations of volume and concentration of hydrochloric acid will result in the highest initial reaction rate for the same mass of zinc granules used? Assume in all cases that the zinc is completely covered by the acid. Okay, if it says to you the zinc is completely covered by the acid, we actually don't care two hoots about the volume, okay? The volume is completely immaterial. The only thing that is material is the concentration, because it said to you the initial reaction rate. If we've got a higher volume of the same concentration, the reaction can carry on for longer, okay? But the initial reaction rate is only going to depend on concentration. Increasing concentration increases reaction rate. So the answer here is B, because that one has very obviously the highest concentration of hydrochloric acid, which means the highest concentration of protons ready to react. Now, number 26, the role of a catalyst in a chemical reaction is to increase the, okay, it does not increase the yield. You just reach equilibrium faster in an equilibrium reaction. You cannot affect how much products you make. That only depends on how much reactants you had. Is the role of a catalyst to increase the activation energy? If it's a negative catalyst, yes. But if they say catalyst, you assume it's a positive catalyst. We need it to. Catalyst decreases the activation energy. It can't be this. The heat of reaction, no. The heat of reaction is only affected by the nature of the bonds and the nature of intermolecular forces in the reactants and the products. So it will increase the rate of reaction by allowing a lower energy activated complex to form, which means that more particles will have activation energy or more, so more effective collisions per unit time can take place. And that is the last question.